All right, so there can be a lot of things to keep track of in these problems, flows in and out, specifications, etc. Sometimes it helps to just get a good idea of, do I understand the whole problem? And so to do that, we have a technique called degrees of freedom analysis, where we analyze, do I know enough about the problem? Do we have everything set? Okay, so this is a tool to help us make it easier. And it helps us count all of the equations and all the things going on in the system. So we want to learn how to do that carefully. So, degrees of freedom, or DOFs, describe the balance between our unknowns and the equations, our unknown variables and the things we know about the system that we're given. It's pretty simple, and I'm sure you've possibly seen this in math or physics class. The degrees of freedom are simply the number of variables minus the number of equations. That's it. So we count the variables, we count the equations. If they match, we should be able to solve things, right? So some terms. If DOF equals 0, we call this a well-defined system, which is what you're used to dealing with. 3 equations, 3 unknowns, it's well-defined, you can solve it. You can go back to your linear algebra. There should be a finite solution, possibly a unique solution. It's possible there's multiple solutions if it's nonlinear, but it should, in this class, you mostly have linear problems that will have one solution. This could come out differently, though. We could have the degrees of freedom could be less than 0, meaning I have more equations than I have unknowns. That can happen. We call this overdetermined. An overdetermined system. It means we've got too much information. It could mean we have redundant information. We've written things down multiple times, and it's actually the same equation, which I think we did on the board. We had some equations come up earlier this week that we said, oh, these are the same equations, same information written different ways. So you could come up with things overdetermined. It helps you sort out which equations you really need. It could also mean you have information that's in conflict. It could mean that you've got inconsistent information that just doesn't match. So that's good to know, because you'd want to know that about your system. Okay, the other thing we'd have is degrees of freedom is greater than 0, meaning the variables are, we have more variables than equations. We call this an underdetermined system. And I think this is the one that actually happens much more often in engineering. We're trying to solve a problem, we know some things, but we don't know a lot. This happens in our research a whole bunch. We want to solve protein folding problems. We start with a sequence, we want to fold the protein. And along a protein, you have many, many bonds that can turn, if you think of your molecular models in chemistry class. So you have all of those are degrees of freedom. So we talk about degrees of freedom in the research lab all the time. If I have an amino acid sequence and I have two angles I can twist in every amino acid, I have 2N, 100 residue protein, I'll have 200 degrees of freedom we have to specify. That's a lot. So it'd be nice to have 200 equations and find the answer exactly, but I don't. So typically there's techniques you can do to deal with this. So in protein folding, what we do is I say, well, the energy should be a minimum, so let me just change all these degrees of freedom and try to minimize some function of all these coordinates. And so by minimizing that and trying all different degrees of freedom, then we can come up with a solution. But it's really exhausting, so that's why we have really good computers. So this comes up very often. So if you're designing a process, it can be the same thing. You can have many, many variables, and you're going to have to maybe, the thing you can do in this class or in process design is just kind of postulate some things. Well, let's set a basis. Let's set a separation value. Let's set some minimum limits. And you just start setting some variables and see how things work out. Okay, this is a ridiculously simple problem. We're going to have a tank, some kind of chemical reactant or product. We're going to have some kind of flow rate in and some kind of flow rate out. How many degrees of freedom in this system? question. It's just a storage tank. 2 degrees of freedom. So I basically want degrees of freedom equals the equations minus the variables minus the equations. How many variables? 2 variables. How many equations? I haven't written any down yet, but we should be able to count them. How many equations? I got stuff coming in and stuff going out. We spent the whole chapter on material balances. How many material balances? Stuff. You can balance the stuff. Stuff going in. Let's see. Maybe I should say that this is at steady state. So there's no accumulation. Otherwise, I'd have another variable there. But yeah, one material balance, one equation gives me 1 degree of freedom. That tells me I can set one of these numbers. I'm free to set one of these. I can set F1, and then everything else will be specified in the system. Right? So if I set F1, we should be able to find F2. That's all degrees of freedom means. The other way around, I could set F2, and that should specify F1. Yeah? Daniel?
Do you count the system variables too, if you're writing that balance equation?
If I wanted to do the unsteady state, then I'd have F1, F2, accumulation. Now I'd have 3 variables minus 1 material balance. Now I have 2 degrees of freedom. Yeah, so if it's unsteady state, I don't know, if I pick F1 and F2, I can tell you how fast things are accumulating. Right? So in a chemical plant, what we'd do is we'd put a process control system. This would be senior year. You take process dynamics and control. We talk about how to link these things together. So we might put in a differential pressure meter here that would measure the pressure here and the pressure here, and from the pressure be able to tell the depth of the water. We would transmit that back through a computer system and then to a valve that would then open and close the outlet valve. And we might let this fluctuate because maybe it comes out of a reactor or a cell system or something that fluctuates and we can't really control. And we'll set this one, so given this, we'll set the flow rate and have that under control to keep the level steady. That might be a thing we would do. We could also put this control system on the front end and let this vary. Maybe it's downstream with that varies, and then we want to accommodate for that. So we'll talk about that senior year in control class. Okay, so she's got 6 steps. Some of them are the same as what we would do for regular problems. Draw a flow diagram, choose a system, choose components, label the diagram to show the components each stream and the accumulation in the system, write down any chemical equations. So this is kind of like the first half of the 10 steps. We're basically writing out the system just so we get a nice picture of what's going on and have labels. And then the difference, instead of going through and actually solving the equation, we just kind of list them out. So in step 4, we're going to count the variables. And then step 5, we're going to count the equations. And then we'll do the 3 F's. This is a slight variation of the problem we did on Wednesday. So ammonia synthesis. A gas mixture of hydrogen and nitrogen is fed to a reactor where they react to form ammonia. The nitrogen flow rate in the reactor is 150 gram moles per hour. This should sound familiar. The hydrogen is fed as a ratio of 4 moles of hydrogen per mole of nitrogen. The balanced equation is nitrogen and 3 hydrogen go to ammonia. Of the nitrogen fed to the reactor, 30% leaves in the reactor output stream. The reactor outputs at steady state. So a question I could ask you is determine the degrees of freedom. I just ask you the degrees of freedom. All I need is the degrees of freedom analysis with enough documentation so I can check that you actually did the steps. And then you don't need to solve the problem if I just ask for degrees of freedom. Step 1, diagram. System. Reactor, hydrogen, nitrogen, ammonia, hydrogen, and nitrogen. With the system will be a reactor. choose components. Components, we'll do molecules, just like we did last week, hydrogen, nitrogen, and ammonia. And then step 3, label the flow diagram, show the components in each stream. So I'm jumping ahead here. So hydrogen in, nitrogen in, ammonia out, hydrogen out, nitrogen out. And any accumulation in the system, is there accumulation? No accumulation, no accumulation variables. Write down any chemical reactions. N2 plus 3H2 goes to 3NH3. 2NH3. Okay? All right, step 4, count the number of independent variables. 4A, count the number of stream variables. What are my stream variables? I've got input streams and output streams. What I want you to do when I ask you to do this, I want to see the documentation. I want to see a picture. I want to see the equation. I want to see the variables written out. So I've got H in, N in, A out, N out, H out. 1, 2, 3, 4, 5. Gives me 5 stream variables. Step B, count the number of independent system variables. This is a little bit tricky, but all you have to do is follow the instruction. The number of independent chemical reactions plus the number of components that accumulate or are depleted in the system. How many chemical reactions? One reaction. How many accumulations? None. That's it. I have 6 variables in this system. Questions? Okay, so there's a little bit of magic there. We're counting 1 per reaction. Why are we doing that? We'll talk about this next chapter in detail. Just to satisfy your mathematical curiosity a little bit, if you remember when we solved this earlier this week, we had nitrogen consumed, we had hydrogen consumed, and we had ammonia generated, right? So we actually had 3 variables in there, but I just gave you 1 variable for the 1 reaction. These 3 variables become 1 when we relate these together. We know that the ammonia generated is 2 times the nitrogen consumed from the stoichiometry. We know that the hydrogen consumed is 3 times the nitrogen consumed, again from the stoichiometry. There's 2 equations, here's 3 unknowns. Behind the scenes, you take 3 minus 2 and you get 1 per reaction. Okay, so this is taking into account the consumption and the generation and the reaction stoichiometry to get 1 degree of freedom. We'll do all the math to get more rigorous with this next chapter. For now, make sure you count 1 degree of freedom per reaction. So.
Wait, could you clarify what an independent reaction is?
Yeah, let's see. If I wrote 2N2 plus 6H2 equals 4 ammonia, that's not independent, that's the same reaction.
But for example, like all the reaction steps leading up to ammonia synthesis, like we've already done those.
So this system only has 1 reaction. So yeah, if I wanted to do the whole plant, which I could do 3 reactors with the 3 reactions, and I could list those 3 reactions, and I would count 3 in my degrees of freedom for the whole plant. We'll talk about that on Monday too. We'll do multiple processes on Monday. There are times when 2 reactions add up to a net react. Like remember the 3 reactions, we also had the net reaction for the whole process. That one's not independent because it's just the sum of the other 3. So if we write these as a matrix equation, there's ways to see if they're independent or not. I think there's an appendix in Murphy for that. It can get tricky if there's multiple reactions that are not independent. It's a little bit of a special situation, but yeah, Troy.
If one product of one reaction feeds into another reaction, is the second reaction not independent?
No, it's a different reaction. As long as the stoichiometry is different. Yeah. There's 2 serial reactions. Like it was the ammonia, and we had gas shift reaction, and what's the other one? The methane reaction. There's three reactions in ammonia. Those would be three, and the products of one and raw materials in the next. So. Okay, let me do equation. Step 5. Same thing. It's broken down into 3 parts. Part A: count the number of specified flows. How many flows are specified here? 2. What are the... It's actually good if we write down the equations here. That if you just write 2, I don't know how to grade that. I don't know if you just guessed, or so please write down the equations. So let's see. The nitrogen flow rate is 150 gram moles per hour. N in equals 150 moles per hour. There's 1. What's the second one? Hn equals 4 times N2. Close. Just jumping ahead a little bit. Part B is going to be stream specifications. 150 moles per hour is a flow. That's a specified flow. 4-to-1 ratio is telling you about composition. That's a stream composition specification. So it's a little pedantic, but it's going to help us keep these straight. So N in over H in is 1 to 4. That's going to be a stream spec. That's in part B. Any other stream specs?
Doesn't our N out have to be 30% of N in?
N out has to be 30% of N in. Is that a stream spec?
Yes.
No, you're ahead again. That's okay. We're going to get the nomenclature here. You're picking out the right thing. Part C is going to be system specs, system specifications. And the thing is, that's telling you about stuff going in versus stuff going out. That's telling you about the system, how much gets reacted in the system. That's your stream specification. 30% of what goes out, let's see, N out equals 0.3 N in. That's going to be a stream specification. Anything else? Okay, let's see. So far I've got 1 specified flow, 1 stream specification, 1 system specification. That's D is material balances. How many material balances? Because if there are N components in the system, there are N material balance equations. How many components? 3. So we've got ammonia, nitrogen, and hydrogen. That gives me 3 material balances. I add these up. 1, 2, 3, 4, 5, 6 equations. 6 variables. The last step, step 6. Calculate degrees of freedom. DOF equals 6 minus 6 equals 0. What does that mean? It's well specified. Which makes sense. This is pretty much the problem we did last week. It should solve. We put all these together. Questions about how to do the 6 steps of degrees of freedom or what they mean? Did I give you? I didn't give you DOFs on the homework, did I? They did? I gave you one? Okay. The DOF is your friend. You're trying to do the 10 steps earlier this week, and you're trying to solve everything, and you're lost, and it doesn't make sense, something contradicts, it's open. The degrees of freedom is your friend, because you go through and you count, and you go, oh, it doesn't work, because I don't have enough equations. And then you go back and you start looking for more equations. You go, well, maybe I have too many variables. And then you go and check your variables. So this is a diagnostic tool for you to help check your work and see what you do. This is your friend. All right?